Hello everyone, welcome to the course on signal systems. This is lecture number 2 and in this lecture we will see what is region of convergence of Laplace transform. So in the last lecture we have seen what is a fundamental equation for calculating the Laplace transform of a signal xt. So after calculation we have seen that there must be some region which is called as region of convergence. So as per the definition of region of convergence, it is basically the region which consists of real part of S or sigma for which the Laplace transform of a signal xt converges. So we have seen that for defining that region of convergence, let's say if R denotes a set in the complex plane, we are talking about the complex S plane which consists of the real part as well as the imaginary part of S. So a set R comprised of all the complex number of S such that the real part of S less than A. So for some real constant A, it is said to be the left half plane LHP. So for real part of S less than A, we have two conditions. One is when A is a negative quantity, that means definitely A will be lying somewhere in the left side. And when A is greater than 0, naturally this A will be lying in the right hand side. But real part of S means we are talking about the region of convergence. So the entire region to the left half of A will be shaded and this will be called as region of convergence. Means these are the values of real part of S or sigma for which the Laplace transform of a signal x converges, means all these values which are lying to the left side of A. Similarly, for the second case, when we have A greater than 0, so again for those values which are lying to the left side of A, means this entire region, the Laplace transform definitely converges. So after that we have the second case when the real part of S is greater than A. We have already performed one question, the right sided signal e raised to power minus at u of t. So we have seen that we have a ROC which is right sided. So again the ROC will be, it's a right half plane. So again we have two cases, one is A less than 0 and one is A greater than 0. Means if A is a negative quantity, definitely it will be lying to the left side and the region will be real part of S greater than A, means the entire region which is to the right of A will be shaded and this will be known as the region of convergence for the corresponding Laplace transform. Similar case is when A is a positive quantity, definitely this will be lying somewhere in right hand side. So the region which will be shaded will be this one and this will be called as the ROC, region of convergence of Laplace transform. So we have seen both the cases when real part of S or sigma is less than A, some constant, and when real part of S is greater than some constant. So after this we want to see some properties of region of convergence. So basically these properties are helpful in deciding that what is the correct region of convergence. So here we'll see that what region of convergence is valid or what region of convergence is invalid. So first of all, the ROC of the Laplace transform x, this is nothing but x of s, capital X of s, consists of the strips parallel to the imaginary axis. Means we have the imaginary axis and the ROC is in the form of a strip parallel to the imaginary axis in the complex S plane. We are talking about complex S plane. So if S is in the ROC, then S plus j omega is the ROC for the real of omega. Means again we have that this is a valid ROC. We will see later on that in between this particular region which is somewhat between minus A and A it's a part of ROC. Similarly, this is also the ROC which is to the right. We will see later on the property. But as we look at the third case, So this part we cannot say this is a ROC, because ROC must be the region of convergence, or it is based on the real part of poles, real part of S, or equivalently we can say it will be treated as sigma also. So this can't be a ROC. ROC maybe is in the form of this one, which is the double sided, we will see later on, or maybe when the signal is a right sided signal. So definitely this type of valid ROC we can see. So this is the first property, that ROC will definitely be in the form of a strips parallel to the j omega axis. Next property, let's say if we have the function, the Laplace transform x is a rational function. The ROC does not contain any pole, very very important. The ROC does not contain any pole, and the ROC is bounded by poles or extended to infinity. Since x is rational, its value becomes infinite at poles. We can see, let's say if we have x of s equal to 1 by s plus 2. So definitely the location of poles is at s equal to minus 2. So if we'll see, if we'll put s equal to minus 2 in x of s, so definitely the value will become infinity. That means we are talking about that at the poles, at the location of poles, the transform becomes infinity. So obviously we can say that x does not converge. So once Laplace transform value is infinite, that means we can say that it is not converging at poles. Therefore, it follows that this is a conclusion that the ROC does not contain any pole. So we have, let's say these are the location of poles and this is the location of poles. So in between we have the ROC. We will see later on. It is example of it is a region for both type of signals, means the signal is a combination of right hand sided as well as left hand sided signal. Next, again to the right we have the ROC, which is also a valid, but if let's say we are talking that the location of poles is somewhat in between, like this, we have some rational function x, capital X, which consists of some poles which are lying in these particular locations, and we have defined this as a region of convergence. So this region of convergence is also not valid. So this is, we can say it is invalid. Next, third property, if a function x is of finite duration, very very important. If the signal is a finite duration and absolutely integrable signal, so the Laplace transform x converges for some values of s. Then x converges for all values of s. Means we can say we are talking about, let's say, some impulse signal xt equals to some impulse signal delta t. So we will see later on that the Laplace transform x of s for this impulse signal is unity. So we are talking about that if a function x is of finite duration and it is basically absolutely integrable, then the ROC is entire S plane. The entire S plane will be the ROC of this particular signal delta t. So we can say that these ROCs will not be possible, means right sided or left sided, they won't be possible here. So this is a valid ROC, whereas these two are invalid ROC, because they are corresponding to some right sided signal and this one is corresponding to, let's say, some left sided signal. So this is the third property of ROC. Now we'll talk about the fourth property, that if a function x is a right sided and the real part of s is equal to sigma is in the ROC of the Laplace transform x of, let's say, some time domain signal which is x of t. This is nothing but x of s. Then all the values of s for which real part of s greater than the location of sigma naught must also be in the ROC. That is, the ROC includes a right half plane containing real part of s equal to sigma naught. So if X is a right sided but not left sided signal, so definitely the ROC has to be a right half plane. So what we have, clearly we can see that if this is a location of pole, let's say, and if the signal is a right sided signal, so definitely the ROC will be right sided. So ROC will be lying in right hand side of S plane. Right hand side means RHP. Similarly means this is somewhat for left sided. This is somewhat for left sided, so definitely it is not a valid ROC. It is invalid. Now we can see this third figure. Here we can see that these are some location of poles and this region was defined as a part of ROC. So definitely we must remember a small point over here, that it is example of this ROC is of both sided signal, means the signal is a combination of both left sided as well as right sided signal. So it will, those type of signal will contribute this type of ROC. But here we are talking clearly about the signal is a right sided signal. So definitely the ROC must be in RHP, right half plane. Similarly, if we'll talk about the fifth property, that if the function x is a left sided signal and real part of s equal to sigma naught is in the ROC, is the part of ROC, then for all values which is real part of s less than sigma naught must also be in the ROC. So let's say this is some point sigma naught. So definitely the signal is what? Signal is a left sided signal. So if the signal is a left sided signal, definitely the ROC will be in the left half plane, LHP. So it has to be real part of S less than some sigma naught. So definitely we have to shade this entire region. This is the ROC. So again, this will be invalid because our signal is a left sided signal, and we are aware that this type of ROC is possible only when we have a both sided signal. We have a both sided signal, means a signal is a combination of right sided as well as right as well as left, means e raised to a minus a mod of t. So for those type of signals we can have this type of ROC. The third case is, we can clearly see that this is what? This is somewhat lying in the right half plane, and we are aware that signal is a left sided signal, means this signal is somewhat u of minus t type, u of minus t, which is a left sided. So definitely this ROC signifies that the signal corresponding to this type of ROC is basically a right sided signal. So if it is a right sided signal, then this is true, but naturally we are talking about the fifth property, which is for the left sided signal. So this has to be a invalid ROC. Next, if a function x is a two-sided, we have talked about left sided, we have talked about right sided signal, now we are talking about both sided, means if the signal x is let's say a both type of signal and real part of s equal to sigma naught, this is in the ROC, then the ROC will consist of strips. The ROC is in the form of a strip in the complex S plane. That includes the line real part of S equal to sigma naught, but does not contain any pole. But does not contain any pole, because we have already seen in our previous properties that the Laplace transform does not converge at poles, it will become infinity. So the poles has to be excluded. So we can see that if it is a both sided, so definitely we have some right sided type and we have some left sided type. So we have that intersection type, and the common region will be this entire one. So if we'll see this one, So clearly this is right hand RHP and this is entire. So entire means entire is possible if we have a finite duration signal and which are absolutely integrable also, right, like some delta t type. So this will be also be invalid, and naturally the entire region, this was entire region. Entire region. So entire region also not valid because entire region was corresponding to some impulse signal type. So next we have the seventh property. If the Laplace transform x of a function x is rational, then if x is right sided, we have talked, the ROC of x is to be right to the rightmost pole. Very, very important. If the signal is a right sided signal, then ROC will be right to the rightmost pole and does not contain any pole. This is somewhat, the property is bit similar what we have studied earlier in property number, let's say 4th. So the right half plane to the right of the rightmost pole, because we are aware if the pole is lying somewhere in the ROC, so definitely what happen, the transform will not converge. Similarly, if x is a left sided signal, then ROC of x is to the leftmost pole, because again the reason is same, at the location of pole the transform does not converges. So if we can see that this is valid because it is left to the leftmost pole. We can see that this can't be ROC because ROC does not contain any pole. Similarly, if we can see this one, so someone has marked this is the location of poles and this is the ROC. But we are aware that if the signal is a left sided signal, so ROC will be left to the leftmost pole, means it has to be this way, means it contains basically poles which is not valid because ROC does not contain any pole. Similarly, this third case, if we have, let's say, we have these are the location of poles and we have marked the ROC which is to the right, so definitely we can say that this is valid ROC because it signifies that the signal is a right sided signal and ROC is in the right half plane, and definitely ROC is right to the rightmost pole. So this is right to the rightmost pole, so definitely this type of ROC is, we can say, valid. But its counterpart, if we start with the region we have defined is this one and our region basically contains a pole, so definitely the ROC must, the ROC does not contain any pole because the reason is same, the transform does not converge. So these are some properties of the ROC. So there are 7 properties. So after this, we have the generalized question over here that Laplace transform x of a function small x has the algebraic expression, identify all the possible ROCs of x, means here we just want to represent, we want to define what all possible combinations of ROCs are possible, and for each ROC indicate whether the corresponding signal or the function x is a left sided but not right sided. Next is we have, let's say, right sided but not left sided, both sided or finite duration. So we have, so whatever the all possible cases for ROC we have to indicate that the function is left sided, right sided, both sided or of finite duration. So what are the steps? So steps are, first of all, we need to find out the location of poles. So to find out the location of poles, first we remember that we need to perform the partial fraction. We need to perform the partial fraction. Using this partial fraction technique, we have to find out the location of poles and we can mark the region of convergence. We have seen in our last lecture that we have a relationship for the inverse transform calculation, but generally we don't use that particular formula directly. Instead, we are using the partial fraction technique. So if we perform the possible ROC associated with the transform are determined by the location of poles of the function. So we must find the location of poles. If we can see, poles are the location of the value of S for which the transform become infinity, and the definition for zeros are those values of S for which the transform value will become 0. So the location of zeros, we can say when numerator equal to 0, this is the location of 0. Similarly, as per the definition, the location of poles will put this equal to 0. So location will be -1 plus j. Next is we have -1 minus j. Next we have -2, and next we have +1. So we have four poles, 1, 2, 3, 4. So as per this, we can say that if we can arrange somewhat in let's say in this particular order, -2 first we have, after that 2 complex we have, and next is fourth pole is a positive pole. So if we can mark the location of poles, so first is -2, definitely -2 will be lying somewhere to the left side of S plane. Next we have the complex poles, which is -1 plus minus j. So -1 definitely this one, and like this. This is the second location of the complex conjugate poles. Next we have, this is real part of S and this is imaginary part of S. So if we can clearly see that what all possible cases for ROC we have. So first will be definitely when ROC is right to the rightmost pole. So as per the property, we have seen that if ROC is right to the rightmost pole, so definitely the signal will be right sided. Next, if we'll say that if the region of convergence is this one, so the ROC is left to the leftmost pole, so definitely the signal has to be a left sided signal. So we have this first like this, second we have like this to the left. Next we may have the region between, we are already aware as per the property that if the ROC is both sided, means between two location of, let's say, poles, so definitely the signal will be both sided. So this will be third possibility and this will be fourth possibility. So as per the location of poles, we have 4 different type of cases. First is real part of S less than -2. Second is real part of S basically greater than -2 and less than -1. So this is first, this is second. Third case, when real part of S is between -1 and +1. This was +1. So this is third case. This is third case. And finally we have the last case, which is right to the rightmost pole. So definitely the signal will be right sided. So later on we have to basically decide on the basis of ROC that whether the signal is right sided or left sided or both sided. So if we can see, as per the location of poles, we have all 4 possible cases. This is first case, and I have marked the ROC over here, that entire we have the real part of S less than -2, means this is left half plane. So as per the property of ROC, if the ROC is left to the leftmost pole and it is lying in the left half plane, so definitely the signal is a left sided. Second case, when the region is we have marked which is between -2 and -1. So as we are already aware, if the ROC is both sided, so definitely the signal is, it's a combination basically which consists of some left sided signal as well as some right sided signal. Next, third case, again we have the ROC which is between -1 and 1. So definitely it is example of this ROC is basically signifies that the signal is a both sided signal. Signal is a both sided signal. The last case, when real part of S is basically greater than 1, so this ROC signifies that ROC is lying in the right half plane and it is right to the rightmost pole, which signifies that the signal is a right sided signal. The signal is a right sided signal. So in this way we can, on the basis of the location of the poles, we can mark the region of convergence for the Laplace transform, and on the basis of that region of convergence we can say that whether the signal is a left sided signal, both sided signal, or it is a right sided signal. So later on we will see that how we can utilize these properties of ROC to explain that when a system is said to be a causal, when a system is said to be a stable system. So after this properties of ROC, we are having properties of Laplace transform. So likewise we have seen several properties we have already seen earlier in case of Fourier transform. We start with the linearity. So linearity means if the signal x1, we have the transform is x1s and we have x2t, the transform is x2s. So linearity is basically the principle of superposition which consists of additivity as well as homogeneity. So if we are multiplying the input signal by a factor of a1, so definitely the transform has to be multiplied by a same factor. So what is the ROC? ROC, this part is quite important. So ROC will be basically the intersection of the ROCs of R1 which is corresponding to x1 and the ROC which is R2 which is corresponding to the signal x2. Next we have, so we are getting a1 times of x1 plus a2 times of x2. After that we are having the second property which is time domain shifting, time shifting. So x of t minus t naught, we are having the equation x of s bilateral Laplace transform minus infinite to infinite xt e raised to power minus st dt. So with the help of this particular equation, we can derive these all properties of Laplace transform. So in this previous equation, we just need to put t equals to t minus t naught and just expand this exponential part. So what we can see that there is some factor which is e raised to power s t naught multiplied by x of s, like this. So definitely if we can see that this is x of s, there is no change in the transform, only this exponential part is further added. So what happened, the ROC will be, means due to time shifting there will be no change in the region of convergence of Laplace transform. Next, this is shifting in S domain. This is quite important. E raised to power s naught t xt, then what is the corresponding shift in the Laplace domain? So as with the help of property we can see that it will contribute x of s minus s naught. So we are getting the ROC which is r plus real part of s naught. Similarly we have the time domain scaling, conjugation. So these property in the next lecture we will see what are the further properties and what are the impact on ROC. So conjugation, time domain convolution, time domain differentiation and so on. So later on we'll see this. These are the references. Thank you.